Hi, welcome back. This is Professor Ridge and today's lesson on section 4.2, graphing polynomial functions. If p of x is a polynomial function of degree n, then the graph of the function has at most n real zeros. Okay, so if it's degree 5, then there's at most 5 real zeros. And thus, remember the connection between real zeros and x-intercepts? So if it can have at most 5 real zeros, then it's going to have at most 5 x-intercepts. And if it's degree n, then it's going to have at most n minus 1 turning points. So peaks and valleys. Or I like to say humps. Okay, so note, turning points on the graph can also be called relative maxima or minima, and that happens when it changes from decreasing to increasing or increasing to decreasing. Okay, so we can go from decreasing to increasing. See, this is a turning point. Or you can go from increasing to decreasing. Okay, so I call them their peaks or valleys or humps, I like to say. Okay, so we got relative maxima or minima. That's another term too. We'll define that one later on. Alright, so to graph a polynomial function, we're going to do the following. Your first thing is you're going to use the leading term test. I forgot to write term test to determine the end behavior. Then you're going to find the x-intercept. So you're going to find the zeros. Okay, so you find the zeros by setting the function equal to 0 and solve it. And then any real zeros are the x-coordinates of the x-intercept. So that's our goal, is find the x-intercepts. Okay, so the third thing is you use x-intercept to divide the x-axis into intervals and choose a test point in each interval to determine the sign of the function values in that interval. You're going to draw the x-axis, you're going to plot all the x-intercepts, and then you're going to pick some point to plot in each interval, and then that also not only does tell you the sign of the function, it tells you whether it's above the x-axis or below the x-axis. One other note, I generally skip this step, and I'll show you the way I do it. I kind of use the end behaviors and multiplicity, and then I just kind of keep track if I'm above or below. Right? So I'll explain more when I do an example. Okay, so you can, again, I kind of skipped that step 3. The next step's real important is you find the y-intercept. So find f of 0. This gives you the y-intercept. Okay, and then if necessary, pick some more points and plot them to help give you additional information about the graph. And then as a partial check, so number 6, as a partial check, use the fact that the graph has at most n x-intercepts and n minus 1 turning points. Okay. Now also multiplicity zeros can be considered to check where the graph crosses or is tangent, touches, or bounces, however you want to say that, to the x-axis. And I actually use that in place of 3. I'm going to use the multiplicities and the end behavior to kind of keep track of where I am on the graph. So I'll show you an example right now. Alright, so let's use this process to graph f of x equals x to the 4th minus 4x to the 3rd plus 3x squared. So my first thing is I'm going to use the leading coefficient test. So actually I interchange 2 and 1. So first I'm going to find the zeros. So find the zeros, or the x-intercepts. So we're going to set it equal to 0, solve for x to the fourth minus 4x. So basically I'm going to do 2 first. So x squared minus 4x plus 3x squared equals 0. So I can factor out an x squared. So I got x squared minus 4x plus 3. Factors of 3 that add to 4. It's 3 and 1. They're both negative. So x equals 0. X equals 3. X equals 1, and I'm going to note multiplicity. So that's 2, 1, and 1. Okay, so my x-intercepts are 2, 0, 3, and 1. And then my leading term test is x to the fourth, so that's degree is even, and a sub n is greater positive, so that means my n's are both going up. Okay, so the zeros are 0, multiplicity of 2, 1, or 3, and 1. Now my n's are going up, so I just kind of lightly sketched this. And then my third thing is, okay, so it says use the x-intercepts to divide the x-axis, which I read. So we have these 4 intervals, and it says to pick test values in each interval to see if it's positive or negative. Well, I don't do that. I just look at leading term. If here at 0, that's the last place it crosses 0, and I know that the graph it can't cross the x-axis unless, you can't change from positive to negative unless you cross the x-axis. So there's no way that from anywhere to the left of 0 that it's going to be negative, because I have to end up here because of the leading term test. So I already know everything from negative infinity to 0 is going to be positive. And then using the fact that the multiplicity of 0 is 2, when it hits the x-axis, it's not going to go through, it's going to bounce. So it's going to do something like this. Okay? So I use that fact. And then at 1, so now I'm still above the x-axis, so it's going to go up somewhere. Then it's going to come down somewhere. And it's going to hit the x-axis at 1, and since multiplicity is odd, it goes through. So it's going to do something like that. And then it's going to go down somewhere, bottom out, turn around, come back up. And it's going to hit the x-axis at 3, and since the multiplicity is odd, it goes through. And then that's the last x-axis, so it can never come back down and hit the x-axis again. Otherwise, you'd have another 0. So then it's going to continue on to the end there. So now I have the basic overall shape. It's kind of like this funny W. Now, if I had some calculus, I can figure out what that relative minimum and relative maximum, or I said it backwards, relative maximum, relative minimum are. But in 105, all I expect you to do is to just pick a point in between 0 and 1, plot it, just to get you a rough idea how high it's going to be. So if we evaluate, so this is kind of like 3, if I do f of 0.5 and plot it, plug it in, so 0.5 to the fourth minus 4 times 0.5 third plus 3 times 0.5 squared, plot it, that can kind of give me a rough idea where that peak is. Again, I would have to do some calculus to figure out what it is exactly, because it's probably not at 0.5, but it could be. And then I'm going to do f of 2 to kind of give me an idea where that bottom is. And again, that's not exactly where it's going to be. It might be, but again, I would have to do some calculus, and we can fill in that last piece of the puzzle there. And I'm also going to do f of 1, negative 1, and maybe f of negative 2. So I don't do it to determine where I am on the graph. I just determine how steep it is, to pick a point in each interval. So f of negative 1. And then I'm going to punch all these in my calculator and plot these points. And then f of, pick one over there, how about 4? So 4 to the 4th minus 4 to the 3rd. That will cancel each other out. Times 4 squared. Okay, so the first one's 0.3125. So that's more like right here. So it does this, kind of. And then I got to do f of 2. Okay, so f of 2 is negative 4. So negative 4 is down here. Now, that's probably not the minimum, but that's good enough for our purposes. It's probably a little bit past that. I would have to kind of do some calculus, and then f of 4 is going to be way off of there. I'd have to do some calculus to figure out what that minimum was. But I can tell you here. I'll tell you. I'm not going to teach you the calculus, obviously, but I'll tell you what the minimum is. It is at 2.36. That'd be negative 4.8. Okay, I'm not going to teach you how I did that. But anyway, you'd use calculus, and that's for the next level. Okay, so then 1.8, and that's off the page, so it's going to really go up fast. And then 4, f of 4 is 48, and that's going to go up real fast. So that's the overall picture. So I'd be pretty happy if you just, understand again, this relative maximum and minimum, it's not at 2, it's down a little bit further. I just want you to get the basic shape, the idea. Okay, this is degree 4. The leading term test tells me what the ends are doing. Leading term tells me the ends. Find the zeros, 0, 1, and 3. Know the multiplicity, so you know if it bounces or goes through. And then just pick a couple points in, a point in each interval to get you an overall idea of how, the shape of it. And the exact bottom and the exact relative minimum and maximums, we'll leave that for calculus, okay? But you just have a basic idea of the shape of this. Okay, so these are kind of rough sketches. And I'd be happy if you could do that really well. All right, let's try one more. So, step 4 was find the y-intercept, which I already found. Right, you put in 0, 0. And then number 5, find additional. So this step 3 is 3 and 5 for me, the way I do it. Okay, so I plot a few extra points, and then I draw the graph. All right, so let's try another one. So let's graph f of x equals negative x times x minus 1 squared times x plus 4 squared. So I'm going to first find, again, I start with my zeros. Find zeros. So that's going to be negative x, x minus 1 squared, x plus 4 squared equals 0. So x equals 0, 1, and negative 4 with a multiplicity of 1, 2, and 2. So now that's going to split my graph up, my x-intercept. So I have the x-intercepts at 0, which will be my y-intercept too, 1 and negative 4. I'm not going to label my y-axis because we're not going to do it to scale. We're going to get a rough sketch of this. Because this is now for the leading term, you just take, ignore, if it's in factored form like this, you just take the first term of each parenthesis to the power and multiply them all together. So the leading term is going to be negative x times x squared times x squared. And just ignore the minus 1, the plus 4. So that's going to be equal to negative x to the fifth. Okay, so the leading term is negative x fifth, so that's an odd degree. And negative. So that tells me my ends are odd degree and negative. They're going up and down. Okay, so now I'm going to combine that with the leading zeros and just keep track of where I am. This is going up. And then in the middle, I don't know. And I go all the way to the last x-intercept to the right. And it's going down from there. Okay, now I go back to look at my multiplicities. At negative 4, we're bouncing. So it's going to do something like this. And again, I don't know how high up it's going to go and how far down. At 0, multiplicity is 1, so it's going to go through. Then it's going to go down. How far down, I don't know. And then at 1, its multiplicity is 2, so it's going to bounce and then go down. So basically, we're going to have this shape. Now, if I want to pick a couple points in the middle, like f of negative 3, f of negative 1, and f of negative 2, and plot those just to kind of give me an idea of that shape. I could also do f of 0.5. Okay, but I'm not too concerned about that. So it's going to do something like this. It's probably going to go down real fast. And pick some points and plot it. So if I did f of negative 3, plug it into my function, I get 3 times 16 times 1. So that's 48. So it goes way up real quick. So again, I'm not going to scale this. It's going to go up real fast, go way up there, come down, and that's good enough for me. I'll go ahead and finish this out. Okay, so anyway, again, the main idea I want you to get, right, so this is degree 5, so we have 1, 2, 3, 4 turning points, because there's a hump there, so 5 minus 1 is 4. It has 1, 2, 3 x-intercepts, because again, it can have at most 5. We got the multiplicity, so that took away from having 5. And then what else? And then again, the overall shape, right? The ends, what the ends are doing. X-intercepts, bounces, goes through, bounces, and then goes down. Alright, so that's graphing polynomials in a nutshell. Takes a lot of practice. And then the last thing in this section is a little discussion about the intermediate value theorem. Okay, so the intermediate value theorem for any polynomial function p of x with real coefficients So suppose that for a not equal to b, so those are x values, a and b are not equal to each other. P of a, again that's a y value, and P of b are opposite signs, then the function has at least one real zero between a and b. So basically we're saying one P of a is positive and the other one is negative, and it doesn't matter which. They're opposite signs. So if we say P of a is positive, so that's above the x-axis, and if we say P of b is negative, now since this there's a property of polynomial functions that they're smooth continuous curves, meaning that we can draw it without picking up our pen. So as we move from left to right, from P of A to P of B, the only way I can connect those dots without lifting my pen is somewhere I'm going to have to cross the x-axis. That has to happen. So there exists at least one number c such that P of c is equal to 0. That's another way that we could write this in notation. So there's 1, 0. Okay, so there has to be at least 1, 0. We could have crossed it twice, 3 times, 4 times. Well, not 3, but we can cross it not 2 times. I mean, we cross it once, 3 times, 5 times, and still connect those dots. So, but we know we have to cross it at least once. There's no way to do it without crossing the x-axis. Okay, so that's the intermediate value theorem. And I kind of call it like the high-low game. So if you find one value that's above, one value that's below, somewhere in between those two is where it's equal to 0. Okay, so we want to determine if f of x has at least one real zero between a is 1 and b is 2. So by the intermediate value theorem, we got to figure out f of 1 and f of 2, see what we get. 1 cubed plus 3 times 1 squared. That's 9 times 1 minus 13. Punch that in my calculator, which I don't have. 1 plus 3 minus 9 minus 13 is negative 20. No, that's not right. That would be negative, okay, so 1 plus 3 is 4. Negative 22 is negative 18. And then we're going to plug in 2. 2 cubed plus 3 times 2 squared minus 9 times 2 minus 13 equals negative 11. Okay, so this doesn't give us any information, because if both of these, if this is A, which is 1, A is 1, B is 2, and both of them are below the x-axis, I can connect those dots without crossing the x-axis. I mean, it's possible. I could go like that. I can go like that. You know, there's lots of different ways. So that doesn't give me any information. So it's not possible to determine. So no, it could, but again, it's not possible to determine. So it doesn't give us any information, right? It doesn't help us. So we need one that's above, one that's below, and then you can say, yeah, for sure, there is one. Now it doesn't tell us what it is, it just says there is one in between those two numbers. Okay, let's try another one. So if A is 1, 2 times 1 to the 5th minus 7 times 1 plus 1. That's 2 minus 7 plus 1 is negative 4. Now we're going to do f of 3 So 2 times 3 to the 5th minus 7 times 3 plus 1 equals, okay, so it's 466. So again, we have one that's positive, one that's negative. So f of 1 is negative, f of 3 is positive, so one's above the x-axis. One's above the x-axis, or f of 1 is below the x-axis, and f of 3 is way above the x-axis. And again, to connect these dots, somewhere I have to cross the x-axis. Now, where, I don't know, but it's somewhere between 1 and 3. So yes, there is at least one real zero between 1 and 3. Okay, there could be 3 of them, there could be 5 of them, but I know there's at least one. Alright, so that concludes the lesson for 4.2. Go to my math lab, complete your exercises there, and I'll see you next time.